What's going on, Science 10s? Mr. Walton here. We're doing another science video. We're talking about rearranging the acceleration equation. So yesterday we were talking about acceleration, and we were describing how it's one of the types of a non-uniform motion. And the acceleration equation was okay. It was pretty standard yesterday. We weren't really doing much with it. We were just kind of focusing on, okay, how can we use this equation to be able to calculate the rate of acceleration? But today, what we're going to do is we're going to rearrange that equation. So to kind of skip to the chase here, of course, the acceleration equation isn't only useful for calculating the rate of acceleration, it's also useful for calculating the amount of time it will take to reach a certain velocity or predict what final velocity an object will have, blah, 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 blah. So let's take a look at the versions of the acceleration equation. The only one you know of right now is the A equals VF minus VI over delta T. That's the only version of the equation you know of right now. But of course, that's not the only one we could get. What we could do, if we really wanted to, there are three other variables that we could solve for in this equation, or isolate for these variables. The first one that we're going to talk about is delta t. Now, that's one that we could rearrange for. How would we do that? Well, pretty similar to what we've done already earlier, okay? So here we go. We're going to do number one. So A equals VF minus VI over delta t. Oh, that's terrible. Oh, man. Oh, that's terrible. Okay. So if this is the variable that we want to get by itself, it's in the denominator. And remember, when a variable is in the denominator and we want it by itself or isolated for that variable, we want to multiply everything by itself. So multiply by delta t, multiply by delta t. You'll see that delta t and delta t cancel, and you're going to end up with delta t times A equals VF minus VI. Now this is really important because this version of the equation, we can do anything from here. There's no denominators. We can either add or subtract, or we can divide or whatever, okay? Now remember, keep in the back of your mind, we want delta t all by itself. So if we want delta t all by itself, in order to get rid of some of the other variables that are beside it, we're going to do the opposite operation. What is the opposite operation of what's happening? Well, this is delta t multiplied by A. So let's divide by A and divide by A. And what we're going to get is we're going to get delta t is VF minus VI over the rate of acceleration. Perfect. So that is kind of our first rearranged version. Ooh, that's a terrible box. Oh, sorry. So that's kind of the first rearranged version. Now let's go back when we multiplied by delta t, right? When we brought the delta t up here, let's go back to that version of the equation, okay? Let's try and rearrange for something else. So we've got delta t times A, or A delta t, as you'll see it written a lot like that, equals VF minus VI. And so the way we're going to go about doing this is if we want to get VF all by itself, what do we have to do? Well, it's being, we're taking VF and we're subtracting VI. So let's add VI to both sides. Let's add VI to both sides. So when you subtract something and then immediately add it, it's like stealing $5 but then giving them $5. You're basically stealing $5 but then giving them the $5 you just stole for them. So basically nothing happens, right? That's not a moral lesson. Please don't take moral advice from Mr. Walton. Okay, here we go. So what do we have left over? Well, on the right-hand side, we got VF all by itself. So I'm going to write that on the left-hand side. I know I said it's on the right-hand side, but you can remember you can just swap sides. VF is equal to, well, now we've got, the way you usually see this is A times delta t, which is the same thing as delta t times A, plus VI. And that is kind of the second version of the equation that we want to deal with. Man, I cannot draw boxes. I don't know what's wrong with me. Goodness gracious. Okay. So these are the two rearranged versions of the equations that we could deal with. Now, there's a third variable in here, fourth variable, I guess, that we haven't solved for. That's the VI, and we're not gonna do that. And the reason why we're not going to do that is because you can focus on that a little bit more at the Physics 20 level if you really want to. So we're going to go ahead and we're going to do our first example problem with this. Got to wait for my computer to catch up to me. Example number 1, how much time would it take for a rocket which starts from rest? Oh my goodness, starts from rest, Walton. Come on, proofread. Which starts from rest and accelerates at positive 20 meters per second squared to reach a final velocity of positive 500 meters per second. No problem. Let's do this. Squiggly line. Let's go ahead and summarize our information. How much time? It's saying how much time. Delta T equals question mark. Would it take for a rocket which starts from rest? That means VI equals 0. VI equals 0 meters per second. Don't need positive, negative, because nothing is just nothing. And accelerates at a rate. So accelerates at a rate of positive 20.0 meters per second per second. So remember, what that means is that our velocity is changing. Acceleration is the rate of change of velocity. It's our velocity is changing at it's gaining 20 meters per second every second. So after 0 seconds, it's 0. After 1 second, it's 20. After 2 seconds, it's 40. After 3 seconds, it's 60. I could go on, but you're really bored of this right now. Okay. VF is 500 meters per second. Positive 500 meters per second. So let's go ahead and do this. If I went back to the versions of the equation that I want to use, should I use the first, regular version? No, I'm not looking for acceleration. I'm looking for time. How much time? I'm looking for VF minus VI over A. But let's just kind of prove to ourselves that we can do that again. So our original equation was A equals VF minus VI over delta T. And if I'm looking for delta T, it's a lot like the velocity. We just swap A and delta T. So delta T equals VF minus VI over A. That's how we rearrange it. And then so you get 1 mark for that. Just remember, you get 1 mark for just writing down the rearranged version of the equation. Okay, let's plug in our information. VF is positive 500 meters per second. Plus, that looks like meter joules, but you know what I mean. Plus, no, not plus, minus. Let me actually do that for me. Minus, what was our initial velocity? 0? You gotta be kidding me. Our initial velocity was 0. That's gonna make us so much easier. Divided by the rate of acceleration, positive 20 meters per second squared. And so let me show you something crazy here, okay? Minus 0, so we just ignore that. Positive 500 divided by 20. Well, the positive and the positive are vectors, and they cancel out. Just like north divided by north would cancel out. 500 divided by 2, oh my goodness. 500 divided by 20, carry the 1, that should be 25. We're looking at 25. We got 3 digits on top. 1, 2, 3 digits on top, and 3 digits on the bottom. 1, 2, 3 digits on the bottom, so we need to round to 3 digits. And what do I get? Meters per second cancels with meters per second, and the second comes up. It's a little bit complicated. That's okay, but we're left with time, and time is always in seconds. That's what I'm talking about. So it's going to take a grand total of 25 seconds for that rocket, which started at rest, right, to accelerate to a final velocity of positive 500 meters per second. Now, if you're bored by T-charts, that's totally fine, but I just want to do something, and I just want to prove to you that we didn't need very complicated math to do that. We didn't need very complicated math at all. If I said time in seconds and I had velocity in meters per second, it's starting at rest, right? So after 0 seconds of acceleration, we're still at 0 meters per second. But every second, we're gaining 20 meters per second. So after 5 seconds, we're already at 100 meters per second. Now, if I kept doing this, blah, 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 all the way down to 25 seconds, you would see, blah, 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 that we would end up with a final velocity of positive 500. So we didn't actually need very complicated math. We just needed to do, like, either rearrange the formula or just do some kind of logic T-chart stuff. Just a couple more examples, and then we'll get you on your way. A racing car. Wow, a racing car. Is that the way you would say that? A racing car. Whatever. Okay. A racing car accelerates at a rate of positive 9.27 meters per second squared for a time of 6 seconds. If the car was initially traveling at positive 10 meters per second, what is his final velocity? His or her final velocity. Squiggly line. Okay. Accelerates at a rate of that. So acceleration pod is 927 meters second squared. Perfect. For a time of delta t equals 600 seconds. If the car initially vi positive 10.0 meters per second. I don't know if you could tell, but I just lost my train of thought because I was doing this stupid thing where I keep saying everything. Okay, what is his or her final velocity? VF arrow question mark. Perfect. Well, what I want to be very clear about is that you do not want to have to memorize all of these formulas. Now, during the whole global health pandemic thing that's going on, you'll have your notes all the time. So you can just look it up. But just the ability to rearrange an equation is super duper duper insanely important. Please, 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 just kind of know how to rearrange these equations. It'll help you a lot. So if we want VF all by itself, we bring VI or delta T up. Okay, so this is going to turn into A delta T equals VF minus VI. And if I want VF by itself, I just add VI, add VI, right? And so my formula is VF equals A delta T plus VI. So let's go ahead and plug in all the information. Here we go. Acceleration, rate of acceleration, positive 9.27 meters per second squared. How much time? 6 seconds. So 6.00 seconds plus our initial speed was positive 10.0 meters per second. I'm running out of room. Uh-oh. So you do this on your calculator. You go 9.27 times 6 plus 10 is going to be 65.62. And because it's a final velocity, right? So basically what's happening with the units is seconds cancels with one of these seconds. You get meters per second plus meters per second. And when you add units, they just add together. So you don't actually combine the units, and you get left with meters per second. That is not our final answer. You got just a little tiny thing, a little thing called significant digits. And so that significant digits is going to be really important for us moving on forward to Chem 20 and Physics 20. So what do we got here? Well, we got 3 digits times 3 digits is going to be 3 digits plus 3 digits is going to be 3 digits. Okay, so when we're looking at this, there's my 3 digits, is going to be 65.6 or 65.7. Are we going to round up or are we going to stay? We're not going to round up. So we are going to have this at 65.6 meters per second positive. 65.6 meters per second. Woo! That's what I'm talking about. One more. We can do this. I believe in you. I have all the faith in the world that we can do this. Okay, here we go. When objects fall, gravity accelerates them at a rate of negative 9.81 meters per second squared. No matter what the object is, objects accelerate at the same rate. Okay? So if you were, that's barring things like wind resistance and stuff like that, okay? We just kind of ignore those right now. So if we were to drop a feather like a bowling ball from the same height at the same time, they would actually fall at the same rate. They would speed up. They would accelerate at the same rate. So if Mr. Walton throws a ball up in the air with a velocity of 25 meters per second, how long will it take for the ball to reach its maximum height? Basically what's happening here is Mr. Walton's going to throw a ball up in the air, and it's going to go up, and then it's going to come down, okay? It's got a velocity here at the beginning of positive. Why do we say positive 25 meters per second? Because it's going up, and we define up to be positive and down to be negative. Now what's going to happen? Where's gravity pulling this thing? Gravity is constantly pulling down on the ball, right? That's the force of gravity. So that's why its acceleration is negative when you look at the negative 9.81 meters per second squared. So what's going to happen? Do you think as this ball goes up in the air, is just for a fraction of a second, do you think it will stop in midair and then start coming back down? Another way of saying that is, what is its velocity right at the very top of this arch? Well, its velocity is 0. It actually comes to rest for a tiny fraction of a second and then drops back down because gravity keeps pulling on it. So let's do our squiggly line. We know the rate of acceleration, negative 9.81 meters per second squared. We know the initial velocity is positive 25 meters per second. We don't know how much time, question mark, but we do know the final velocity, right? It goes up with a certain velocity, and then it's going to stop in midair, and then it's going to come back down. So its final velocity at the top of the arch is 0 meters per second. I know it's crazy, but just kind of work with me on that. So if we're looking for delta t, let's go back to our original equation, Vf minus Vi over delta t. If we want delta t, remember we just need to swap delta t and a. Whoop, whoop. And we're going to get delta t equals Vf minus Vi over a. And then we just plug in all our information. Vf, what's Vf going to be? 0 meters per second minus negative, nope, not negative, positive, what was the initial velocity? 25 meters per second divided by, and the rate of acceleration is negative 9.81 meters per second squared. Now, it is actually pretty critically important that we get used to having, negatives in here. So what's 0 minus positive 25? Well, that's just negative 25 on top divided by negative 9.81. The negative and the negative are actually going to cancel out. And so that's going to be important a little bit later on. Here, let me just do that in a different color so that people looking at the notes kind of understand a little bit more. Okay, so I brought out my illegally downloaded calculator. So let's put this in. We got two numbers on top. Let's just double check and make sure everything's going to be okay. We got two numbers on top, one number on the bottom. So I'm going to put brackets on top. 0 minus, it's a positive, so I don't need to put it, 25 meters per second divided by a negative. So I'm going to put negative 9.81 meters per second squared equals We're going to get a positive. See, I told you those negatives were going to cancel out. You didn't believe me. That's okay. So we got 2.54841. 2.54841. And the meters per second cancel out, and we get seconds because it's time, so seconds left over. But we got to round to the appropriate number of significant digits. So let's round to the appropriate number of significant digits. We got 2 significant digits on top, 3 significant digits on the bottom. 2 digits divided by 3 digits, we got to round to 2 digits, so 2.5 seconds. That's how long we expect that object to take before it hits its maximum height. Its maximum height is at 0 meters per second. So what I want you to do is try some of these questions. I want you to try, there's 3 questions here. Check the key. Let me know if you have any questions or whatever. Let me know how I can help. And then what we're going to be doing a little bit later on this week, I'm going to give you more practice, and then we're going to do an assignment. We're going to do an assignment based on the stuff that we've already done so far, okay, in the physics unit. So significant digits and scientific notation and velocity and speed and this. So let me know if you have any questions. Hit me up on the Google Meet on the office hours. Other than that, yeah. All right. See you later. Have a great day.